Okay, let's get started. Um, Hopefully you've seen the next homework and got started on it already. So your um, TAs will walk you through the homework uh, at the recitation today. And if we don't finish, then we will finish up the discussion in the next lecture. Okay, so don't be concerned uh, if you don't get through the homework today. So before we start, any other questions? So I'll say the same thing that I say at the beginning of every class. Yeah, I don't have to say it. Great. Thank you. How do you prove two sets have the same cardinality? So in the homework, it gives you examples, right? So there are two proof techniques that are described. Uh, and you can see that for countable sets, there is a somewhat simpler technique. And for uncountable sets, then you basically show a mapping that's a bijection between the two sets. Okay, so if you have a complete matching, as I sometimes call, right? So you have a one-to-one pairing that covers every element, then that shows you that the two sets have the same number of elements, right? So there is an example of each type of proof in your homework, so you can use that sample to solve the other problems. So again, information like the timing of the midterm is going to be posted on the course web page, so that's where you should look. Any other questions? Okay. I can, I can certainly fit many more people on my screen. So please show yourself. Let's try to pretend that this is like regular class. Okay, very good. So in the last lecture, we were talking about graphs and we defined some terms. So let's review these terms and then go from there, right? Uh, um, so a graph consists of uh, vertices, which are called V, right? So sometimes we call it V of G to denote that it's the vertices in the graph G. And then we have edges, which are, denoted using the notation E. And the way the edges are represented is basically the way we represent relations, right? So when we say, uh, uh, if you say Vj is related to Vj plus 1, then we would say the same thing by saying that, the pair Vj comma Vj plus 1 is included in the set of edges, right? So we just draw an arrow between the two vertices that are related, right? So a graph is simply an alternative way of representing a relation, okay? A directed graph specifically is a way of representing a relation. And then once you have a graph representing a relation, then we can start defining operations on graphs, such as you know so if you have graph, then so we can have right? So that's a graph, and it has how many edges? 5, 7 edges. So the relation has 7 pairs of the form Vj comma Vj plus 1. Okay. So once we have represented it in this way, then we can think of operations like walking through the graph, and then we can say a walk is simply a sequence of edges that you traverse, right? So those edges must be adjacent to each other, right? So here is a walk that has 3 edges, right? And a walk with 3 edges will traverse 1, 2, 3, 4 vertices, right? So a walk starting at V1 and ending at Vn will have a length of n minus 1, okay? Now, we have the notion of a closed walk, which means that you start and end at the same vertex. And we say a walk is a path if you don't visit any vertex more than once. So for instance, this is an example of a path, right? In this particular graph, I guess everything is a path because there's no way to come back to the same vertex, because the way the arrows are oriented, you can only go in a sense forward. You cannot come back, right? So, but if you added, let's say, another edge like this, now you can think of taking this edge, then this edge, then coming back here, then going this way, and then that way, right? So if you did that, then you would have visited these 2 vertices more than once, and therefore it would not be a path, right? So that's the notion, that's the distinction between a walk and a path. Whereas even though you went through this multiple times, that will still be considered a walk, right? And a cycle is a special type of, it's almost a path, right? So if you just ignore the last step, then you have a path, right? So V1 to Vn minus 1 is a path, and Vn happens to be the same as V1, right? So it's so those are the notions, and we gave some examples last time, and I gave you an example now, and then we made a few observations. The shortest walk between 2 vertices is a path, because if you revisit the same vertex more than once, that means you are doing unnecessarily going in a circle. So you avoid that, and then you will get to your path. Okay, and just extending that, a shortest closed walk through a vertex is a cycle, right? Because again, if it's not a cycle, that means it must be a path. It must be a walk that visits a vertex more than once, which means it's doing unnecessary work. So, and then we can define the notion of a distance as the length of the shortest path between U and V, right? So given a 2 vertices U and V, you can ask what is the distance, and that's the same thing as the shortest distance or the shortest path between the 2 vertices. Okay, so so now graphs have a number of applications, and we use them. In computer science, we use them quite a lot, right? So can you think of some applications that you may use on a daily basis, or you come across in real world that are basically based on graphs?
Probably something like Google Maps.
Right. So maps are all based on graphs. So you represent cities and distances using graphs. So basically, each city will be a vertex, or each location, intersection, house, right? So depending upon what detail you are seeing in a graph, in a map, uh, your vertices will correspond to that level of detail. And then the edges between those vertices essentially denote things like roads and so on, right? And then there are, so in these graphs, there is some additional information associated with both the vertices and the edges, right? So the vertices, for instance, they may have an address or a longitude and latitude location, right? Similarly, edges have information such as, how long is this edge, right? Is it 100 feet or 500 feet or 3 miles, right? And it also has information like, if you're talking about a GPS system you're using for driving, then it's going to tell you, other information like, is it a 2-lane highway, or is it a neighborhood road? What is the speed limit? All kinds of information can be added on top of this graph, but the basic data structure is basically a graph. So what are other examples of applications of graphs that you can think of? It doesn't have to be necessarily have to be in software. So how do you design a network, right? So your network on which you communicate is, again, thought of as a graph. And when you have a problem of finding the best route for transmitting internet data from your home to Zoom's data center, where these calls get completed. So that is essentially a shortest path problem in graphs, right? So that's how it is formulated, and that's how it is solved, right? So or if you think about electrical transmission networks, once again, they are modeled as graphs. And when somebody is trying to design what is the most efficient or cost efficient way to lay a cable, they are solving a graph problem to find the shortest paths and things like that. Okay, so graphs are the most widely used modeling tool and data structure in computer science. Okay, so what we do here in this course is to just give you a very, very small introduction to graphs, and you will see graphs again and again in many courses throughout throughout your degree. So the last thing we were discussing when we finished up our lecture last time was Euler Tour and Hamiltonian Tour, right? So sometimes they are called circuit, sometimes they are called tour. They all mean the same thing, right? So an Euler tour is a closed walk that visits every edge in the graph exactly once. Okay, so very often when we do Euler tour, we generalize the notion of a graph a little bit, because so far we have this idea that given any two vertices, there could be one edge going this way and maybe another edge going this way, right? But when we talk about Euler's tour, we allow multiple edges between, so for instance, we could have 3 edges going forward and 1 edge going backward, right? So so the Euler tour becomes more interesting if you allow this generalization. Okay, not that you must have this type of a graph. Any type of graph is fine for studying this problem. But when you look at problems involving Euler's tour, I will typically have graphs where there are multiple arrows going forward and backward between any two vertices. Whereas the way we define graphs here, it's like a relation. And so if Vj and Vj plus 1 are related, we will just say it once, and there'll just be one edge from Vj to Vj plus 1 in that setting, right? So we are generalizing graphs a little bit here in order to talk about Euler tour, in order to make Euler tour interesting in relatively small graphs. So let's take an example. So so can we find an Euler tour in this graph, right? So we want to traverse all the edges once. So let's try. Huh. So there we have, okay, I guess no, wrong color. Let's try. So, so we can go this way and that way. So we traversed all the edges once, and we reached the initial point. So that is an Euler's tour, right? So let me undo that so that you can see the original graph and redo it so you can see how the tour is ended, right? So there is a simple, necessary, and sufficient condition for the existence of an Euler's tour, which is that in degree equals out degree. Okay. So by the way, Euler is a very famous mathematician who lived in the 1700s, and most of you know E, right? E, that the base of the natural logarithm, right? So that constant E is named after Euler, right? And Euler did a lot of work, and he worked on graph theory. He worked on Taylor series and those sorts of problems in calculus. So so his name is something that you're going to find in a lot of places. So let's come back to understand why this is true, right? So if the in degree is equal to out degree, then why should it be the case that you can always find an Euler's tour, right? So here is a way to think about it, right? So if at every vertex, your in degree and out degree are the same, what that means is that, think about a vertex V, right? So this condition means that whenever you arrive at V, there should be a way to get out of V because, the in degree and out degree are matched, right? So every time you arrive at a vertex V, you should be able to leave it unless you have already used up every edge out of vertex V, right? So if you arrive at V and then you have used up all the edges, that means you basically completed a circuit, right? So because think about this. Um, so you have a V, and let's say, so let's say that you already traversed this edge, okay, and you have traversed this edge, and then you're going somewhere in the graph, and then you come back here, right? So there must be a way to get out at this point, because you have come into the vertex V using two edges. Therefore, this condition requires that there be one more edge, um, that's there. So you come in for the second time through this edge and you can leave, right? And let's say you go around and let's say so every time you come back, you can say, well, if I was able to come in, then I should be able to leave, right? So the difference comes just in one place. This is a vertex X where you start your tour, right? So if you start your tour, then when you come back, it is possible that you reach here and there is no way to get out, right? Because you already exited this vertex. So when you come back, there is no more, nowhere to go. So now whatever you're covered is a closed path, right? So that's kind of gives you a sort of an idea as to why, when this condition is satisfied, you can keep moving forward until you complete some kind of a circuit, right? Because the only way you can stop is you can stop at a node where you started, okay? Now, this doesn't mean that you have covered everything in the graph. So let's try to add more detail here, or maybe let's take an example that'll make it easier to see what can go wrong if you just try to. So let's say you have right. So let's call this A, B, C, D, E, F, G, H. Then so what could happen is that you could go, wow, okay, I need to get this. Okay, so you could start here, go this way, and then here you could decide to come back and then finish here, right? So now you have a circuit, but you have not visited all the edges in the graph, right? But this is okay, because what you can do is you can, if you haven't finished the graph, that means there must be a vertex like C, which you have visited and turned back from, but has more edges coming in and going out, right? So what you can do is you can then start a separate walk here, right? And then now you go and complete this. Okay. Now you can see that you can stitch together these two circuits into one bigger path, right? Because instead of coming, instead of going to C and coming back to H, you can instead go from A to B, B to C, C to D, E, F, G, H, back to A, right? So you can construct these two little tours and stitch them together into one larger tour, right? And you can keep doing this until you have covered every edge in the graph. And that's why the moment you have this condition, you are able to find an Euler's tour, right? So what this condition tells you is that if you look for a tour and you traverse the graph, then the only place where you will have to stop is the starting point itself. Because at every intermediate node, you can argue that you came in through an in edge and there should be a corresponding out edge. So at every intermediate node, right, if you didn't start at that node, you should be able to come in and then leave, right? So as a result, you can keep going until you get back to the starting vertex, right? So that's what, so this one guarantees that once you start from some vertex, you can keep going forward until you come back to your starting point, right? Now, then you may have come back to a starting point without visiting every edge, in which case you can simply find another tour and stitch them together. And at this point, well, it is possible that what you really have is right. And then you can say, hey, okay, I have one more you know time I can try, and I can finish this. And now I can stitch, all 1, 2, 3, all of these circuits together, and then I'll get one big Euler circuit, right? So you can keep doing this until every edge in the graph is covered. Any questions?
Professor,
Yeah.
I was wondering for C and G why you labeled the vertex with like 2 different letters.
That's because I'm not thinking straight. Okay. Thanks for pointing out.
Okay. And okay.
Yeah. So my mistake. Okay. Yes. So again, when you notice these mistakes, don't think they are small mistakes and no need to point out, because small mistakes that I make are often confusing, right? Because when you're trying to learn something, small mistakes are going to just confuse the hell out of you. So when you find these mistakes, please let me know and I will, correct them. Any other questions? Okay, so that's Euler's tour. And again, it seems Euler's tour is very easy to find. You just keep doing this mindlessly. And when you come back to the starting point, then you find another place to start, and then you keep doing that. So this seems like a very efficient method to find the circuit. Okay, Hamiltonian Tour is sometimes the problem is also called a traveling salesman problem, because what you have is, you can think of it as, as a salesman trying to, tour several cities on a sales trip. So maybe let's call them, cities A, B, C, D, E, F, and there may be many roads between them, right? So maybe not every pair of cities is connected, but some are connected, and some are not connected. And then what the traveling salesman wants to do is the salesman wants to visit every city and do it without visiting any city more than once, right? So so one way to do that is, well, go from. So now I'm using undirected graph. So you can think of an undirected edge as a pair of edges, one in each direction, right? So that is a tour that visits every city once, and doesn't. So it's basically going to be a cycle, right? So it's going to be a cycle that visits every city or every node in the graph, right? So that's called Hamiltonian Tour. And although in this example, it seems very easy to find a Hamiltonian tour, in general, Hamiltonian tour is a very difficult problem, right? So it is what is called an NP-complete problem, right? So we talked about, Boolean. Okay. Boolean satisfiability. Right, so we talked about Boolean propositional satisfiability problem, as we may call it in some cases. So we said that's a very hard problem, and that is also an NP-complete problem, right? So, and this is Hamiltonian Tour is another example of NP-complete problem, okay? So that doesn't prevent people from trying to find solutions to it. And then there are actually variants of Hamiltonian tours that do have somewhat efficient solutions. So for instance, there is a version of Hamiltonian tour called Euclidean Hamiltonian tour, which refers to Euclidean is refers to a notion of distance, and it basically corresponds to the way we measure distance, let's say in the physical world, right? So if we are talking about graphs as representing, let's say, cities in the world, and these edges represent, say, air travel routes, then it's called an Euclidean Hamiltonian Tour problem, and that can be solved somewhat efficiently. Okay, but in general, Hamiltonian Tour problem is NP-complete, and there is no good solution to it. Although, again, it sounds very much like the Euler's tour, but Euler's tour has a very simple condition for the existence of Euler's tour, and once that condition is satisfied, finding the Euler's tour is trivial, whereas finding the Hamiltonian tour is a very difficult problem. So any questions on this?
So you had mentioned that finding the not the Hamiltonian, but the Euclidean Euler, yes, so the Euler circuit, very trivial, but isn't it the same approach as just trying everything until it works?
No.
No,
because see, remember what we did, we never had to go back and retry anything, right? In here, right? We said, okay, so we will do this, and maybe we didn't complete everything, so we are going to just start at another vertex and do this, right? We are never going back and redoing any circuit, right?
Okay, yeah.
That's a big difference. So this one, basically, you're going to spend time that's basically equal to the number of edges in the graph, right? Because you have to try every edge once, but you're never going to say, oh, this is a bad edge, I'm going to come back, I'm going to discard it and come back, right? Every edge you pick is the right edge.
Okay.
Right.
Yeah.
So therefore, you never have to go back. Whereas here, you can easily see that if the way I have drawn the graph, you have an intuition as to how to draw the Hamiltonian tour. But if you're just looking at a graph as a bunch of edges, then you may start going this way, then this way, and then realize, hey, I made a mistake, because if the only way I can go is this way, and now I have completed a circuit and I haven't visited most of the cities. So then I say, hey, okay, I'm not going to do this. This is wrong. So I'm going to go back and try something else, and maybe I'll try this, right? And if you try this, well, that's wrong, because now you can never because now you have gone this way and this way. The only way to get to D is this way, and then you'll have to come back here, and you haven't completed the tour, right? So you have to say, okay, this is wrong, and this is wrong, right? And then you have to backtrack, come back here, and then maybe try this and go here, and then again you may make a mistake and go this way, right? And
Right.
then realize that it is wrong. And so so you have to repeatedly try and fail, and this is where this exponential behavior comes in, because you have to try, uh, you know, as in this case, right? So we went this way, we went this way, we went this way, and then we went this way, and then we realize a lot of things are wrong. So we have to redo, we have to backtrack several steps and then try every other possibility at each step. So essentially, that's when you have an exhaustive search, because at every point in the tour, you're saying, hey, I have, 10 more edges to try, but then I have to try every one of them because I have no idea how to pick which one is going to get me to my tour. So you essentially try all possible combinations, and then that's why it ends up being very difficult.
All right. Thank you, Professor.
So all of you will be taking this AMS 301, I believe. I get confused with this with the number. So most of you will probably take it either next semester or the following semester, and they will cover quite a bit of graph theory in that course, right? So they will you will learn about Hamiltonian tours, and you'll spend a lot more time on Hamiltonian tours than you may want to, but that's coming up in a future course. So again, I want to just sort of give you a few points because the way the way you remember concepts is by making connections across different courses, because the concept connects and has an impact on multiple things that you learn, and that enables you to remember the concept better. And the second way you remember a concept is because it's repeated over time, right? So you know about graphs now, you'll know about graphs in the next semester, then you will come across graphs in the algorithm course, then you'll come across graphs again in the networking course, and so on. And through all of this, you will remember graphs very well for the rest of your life, hopefully. So okay, so that's what I wanted to say about these tours. Now let's get back to what we were talking about, which is relations, because we were thinking of graphs as a more compact way and a more visual way to represent a relation, right? So so let's go back and ask these questions about what some of the things that we learned in the context of graphs, such as walks and lengths of walks. What exactly do they mean in terms of the relation? Right? So let's start with a simple graph. Let's say okay, so okay, so this represented as a graph, if we represented this as a relation, we would say the relation R consists of the pairs A comma B. So each edge will be a pair in this relation, right? So B comma C, then E comma C, C comma D, C comma F, and F comma G. Right? Did I miss any edge? I have all the edges, right? So again, many of you have turned off your cameras. Can a few of you turn it back on? Okay, so okay, so now let's look at walks of length 2, right? So for instance, A, B, C is a walk of length 2, right? Similarly, E, C, F is a walk of length 2, right? So what can we say about walk of length 2 in terms of the relation R?
You're applying the relation twice.
Right. So this is the same thing as R squared, right? So R composed with itself, which means that you take one R edge and then another R edge. So that's what R square means, right? So walk of length 2 denotes R composed with itself once. And similarly, you can understand that a walk of length n is going to be representing R to the power n, right? So again, you can, so in this case, the longest path in this graph is what length? What's the length of the longest path in this graph?
4.
It's 4, right? So what that means is R to the power 4 will consist of what pairs? What are the pairs in R to the power 4, right? So we have these pairs in R. What are the pairs in R to the power 4?
A, B, B, C, C, F, F, G.
No.
It's not.
A, G.
No, it is. So you must have a walk of length 4, right? So that means there is only one, which is A, G. Okay, because if you start, right, if you have to apply R 4 times, right? So it's not that you apply R 0, 1, 2, 3, or 4 times, right? You apply R 4 times, right? So which means that you have to go forward 4 times. And the only way you can do that is if you start at A and then you end up at G, right? So what about R to the power 5? What are the pairs in R to the power 5? Well, there's only one guess, so you can make a guess, and if it's wrong, we can, learn from it. Yeah, Joseph.
Isn't there nothing? Isn't it just an empty?
Yeah, it's an empty relation, right? So R to the power 5 is an empty relation. So now what happens if I, add an edge like this? Then what's going to happen? What's going to be in R to the power 5?
Would it be AF?
Okay. AF, and what else?
Could it potentially be FF? Start at F, go through G, end up at F again. All right, never mind. That was dumb. Never mind.
The number doesn't FF will be there in R to the power 6.
I think it'd be FG and GF.
Right. So you could have FG, GF, and what else?
EG and BG.
Right. So 1, 2, 3, 4, 5. Right. So EG. Right. Because you can do 1, 2, 3, 4, 5. Okay. So the point is that once there is a cycle, then you can use the cycle to go round and round to find many more pairs like this. Right. So that's all I was trying to point out. So again, the walks of length n corresponds exactly to R to the power n. And what this means is that when we ask you a question about composing R or finding R to the power k, the easiest way to do that is to first draw R as a graph, and then its graphs are somehow very intuitive, and it's quite easy for us to quickly answer these questions when we look at the graphs. Whereas if you are asked R to the power 5, and you have to enumerate this by looking at this list of pairs, right? It's going to take you forever if you have to compute R to the power 5 by looking at these pairs and then saying, hey, R is this, R square is this, R cube is this, and so on. It's going to take a lot longer than drawing a graph and then operating using this relationship between walks in the graph and the composition of relations. Okay.
How did you get EG?
EG. So 1, 2, 3, 4, 5. Right? It's a walk, not a path.
Okay.
Okay, good. So what do paths correspond to? It's a little difficult to say. Okay. Paths do have some relationship, but it is not a simple equality, right? So if there is, let's say, a path of length 3, right? So let's take A to D, right? There's a path of length 3 from A to D. What you can say is that R to the power 3 will contain this path, right? We'll capture this, but you won't know whether it is a path or not by just looking at R to the power 3, because R to the power 3 will also contain, C, F, G, F will also be in R to the power 3, and you can't tell, okay, is there a path of length 3 from C to F, right? So what I'm saying is that when there is a path, it's somehow represented in the corresponding relational composition, but you can't really tell just from that whether what you have is a path or not. It could be just a walk. So now we are going to talk about some properties of relations. So a relation is said to be reflexive if every element is related to itself, right? So for all elements, you have the condition that the element is related to itself. So if we draw it as a graph, then let's say we have 3 elements, A, B, C, and you may have these 2 arrows. But if it is reflexive, then you should also have, A connected to A, B connected to B, and C connected to C, which means that every node must have a self loop. Okay, so many relations that we come across are reflexive, and the most common one is equality, right? So when we talk about equality, we of course say, A is equal to A for any A, right? So so reflexivity is a property that we know and understand internally, although we don't, you may not have, seen it stated in this abstract form, but it is a very much a familiar property, okay? And the opposite of reflexive is irreflexive, and irreflexive means that there are basically no self loops in the graph, right? So there shouldn't be even a single self loop, whereas if you say reflexive, then there has to be self loop at every vertex in the graph. Any questions on this? Okay, so let's, the second common property we talk about is symmetric, right? So symmetric says that if A is related to B, then B is related to A, right? So what this means from a graph perspective is that, so let's say we have this. Then what this says is that whenever there is an edge from A to B, I should have an edge from B to A, right? So which means that every one of these should have arrows in the backward direction, right? So all edges should be paired, right? One in the forward direction, one in the reverse direction. Then that is what we call as a symmetric relation. And when you have a symmetric relation, we can avoid the clutter and simply, draw basically a graph with undirected edges, right? So we can say, I'm going to put an undirected edge like this, an undirected edge like this, an undirected edge like this, and I can take these edges forward or backward, and you can see that this is a lot less clutter and much easier to see where you can go from where as compared to this representation, right? So a symmetric relation can be represented more compactly with undirected edges. Any questions? So you can also have what is called an asymmetric relationship, which says that A or B implies B is not related to A, right? So it's the opposite of symmetric, right? So that's called asymmetric. And very often we don't, which basically means that anytime you have a forward edge between two vertices, you cannot have a backward edge, okay? But in practice, we don't often use asymmetry, but we instead talk about antisymmetry, which is a slight twist on asymmetry, because what it basically says is that it gives you one exception to this rule, right? And that is in the case of self loops. It says that if A is related to B, right, either B should not be related to A or B and A are the same, right? So for instance, we can draw this graph. So this is an example of a relation which is antisymmetric, right? It satisfies the condition of antisymmetry, but it doesn't satisfy the condition of asymmetry, right? Because asymmetry simply says, now this self loop violates asymmetry because if you just substitute A equal to B, you need the condition that because B is related to B, we want the condition B not related to B, right? So this kind of makes no sense. So we generally talk about antisymmetry, which basically says ignore the self loops, but otherwise, if you have a forward edge between two vertices, you should not have a backward edge, and vice versa, right? So that's antisymmetry, and that's the condition that we often come across. So can you think of a relationship that we use in our math every day that has antisymmetric property? Some relationship that we use every day.
Greater than?
Sorry?
Greater than?
Can you be more precise?
Like if A is greater than B, then B is not greater than A.
Right, but the antisymmetry relation. Okay, that's a perfectly good answer. I was, for whatever reason, looking for greater than or equal to, right? To explicitly acknowledge the fact that equality is allowed, right? But your answer is, 100% correct. So there's nothing wrong with your answer. So greater than is an example. Greater than or equal to is an example. Anything we think of as ordering, right? So subset are equal to, right? So that's an example of antisymmetric relation. So antisymmetry is something that we come across very, very often, okay? So now let's talk about transitive relation. So a transitive relation says that if you can go from A to B and then B to C, then you can go directly from A to C, right? So, so in terms of a graph, if we draw A, B, C, then what it says is that if I have an arrow from A to B and then another arrow from B to C, then I should also have an arrow from A to C. Okay, so that's what a transitive relation is, right? So you can apply it to larger graphs, and you will see that it just becomes so if this relation were transitive, then we must have all these additional edges, right? So because you can go from A to B and then B to C, therefore I must have an edge from A to C. Similarly, I must have this edge, I must have that edge, I must have that edge, I must have that edge, right? And then I must have this edge, this edge, this edge, and so on, right? So you can see that essentially a lot of nodes will have to have edges between them in order for the relation to be considered transitive, right? So can you think of a transitive relation once again? Anybody wants to, Greg?
Also greater than?
Right, so greater than or equal to, again, subset, all of them have a transitive, relation, transitive property, right? So again, transitivity is something that we come across, very often, right? So that's summarizing all of them in one slide, all of those properties in one slide. So sometimes you start with the relation that does not have these properties, and then we can make the relation have that property by adding what is missing, right? So that's called a closure. So for instance, we can start with a graph and we can do a reflexive closure, which means that we are going to add self loops at every node, right? So when we do that, we have applied what is called a reflexive closure. Okay. So similarly, we can start with, let me. Now I can apply symmetric closure, which says that whenever I have an arrow A to B, I'm going to add a B to A arrow, right? So I'm going to add this, and then this. Now I have done what is called a symmetric closure, right? So, and then we can define what is transitive closure, right? Which, let me again undo and then show it. Okay, so now a transitive closure in this case will be addition of edges that are implied by the transitivity property but aren't actually there, which means that in this case, you can go from A to C and A to D, right?
I have a question.
Yeah.
Is there such thing as like removing edges to fulfill the properties?
No. I mean, okay, of course it's, you can define it, but a closure means adding edges, right? So whenever we say a closure operation, what we are talking about is adding additional edges to get that property. Okay, so let's erase this and try something here. Okay, so let's start with a different graph. Okay, and we will. Okay, so right, so we can apply these closures in different orders, and sometimes we get different results, and there are other times when you'll get the same result. Okay, so let's take, for instance, okay, so here, let's say we first apply symmetric closure, right? So then we get those three, and right? So that's symmetric closure. Now let's do transitive closure on symmetric closure, right? So we take this graph and we do transitive closure on that, right? So then we'll have I have to draw the original graph, and then I will add the new edges. Okay, and if you did this in reverse, what would you get? That is, if you applied the transitive closure first and then the symmetric closure, what graph will you get? You can take a minute to do it. I mean, you can try to work it out on your piece of paper and then tell me if you will get the same result or a different result. Okay, someone says same result. Anybody has a different result? No, nobody else wants to say anything? Right, you just have to do this in reverse. So let me do it in reverse, right? So that way, so we start from this one. Okay, let's do the transitive closure, which means we are going to add that edge, and that edge, right? And now we are going to do the symmetric closure, which means that every edge is going to be reversed, okay? And I'm not so sure that you're going to be able to tell it's the same thing by looking at the result, but you have to sort of try to understand what these, essentially where the arrows are. Essentially, there are arrows between, you know, every pair, you know, along this line, right? And so the result is the same no matter, you know, in which order you apply in this particular graph, but that's not true for all graphs, okay? So because it's quite, why don't we just simplify this graph further, right? So let's just say there are only, let's make sort of a very simple graph, okay? So this is something that we can probably work with without, so on this graph, if you apply transitive closure, right, you get nothing, right? Because you can go from A to B, but you cannot go anywhere from B, right? Same way you can go from A to C, but you cannot go anywhere from C. So there is no way to apply transitive closure. So if you apply transitive closure, you will just get the same graph. Right? Now, if you apply symmetric closure, you are going to get symmetric closure on top of transitive closure, then you are going to get right? What do you think you will get if I apply symmetric closure first and then transitive closure next? Oh, Greg?
You get something different where every vertex is connected to every other vertex.
Right. So basically what's going to happen is that if you apply the symmetric closure first, then you are first going to have this. And now what happens is that after applying the symmetric closure, you can see that every vertex is reachable from every other vertex. So when you do transitive closure on this, then you're going to have these two edges, right? Which are not there in this case, right? So the order of applying the closure operations can make a difference sometimes, okay, in some graphs. Okay, on some graphs, they will not make a difference. And if you spend enough time on it, you'll get some idea of, if you spend a few minutes thinking about it, you'll get some idea when things are going to be different and when it'll be the same. There's a homework problem that's related to this, related to what I just discussed. So hopefully this discussion will get you started on that problem. Okay, so okay, so this is all saying not saying too much. So let's summarize. Let's talk about two other types of relations. Okay, so one is called a partial order, right? A partial order is a collection of other properties. So in particular, you need antisymmetry and transitivity. Okay, then you get what is called a partial order, right? So you need both properties. Okay, so once again, can you tell me something that's a partial order that you're aware of, some relation that we use, we come across every day? I'm sure the answer is boring, but still it's okay to say the answer. So what is an example of a relation that we use frequently that is both antisymmetric and transitive? That must obvious, I suspect everybody in the class knows the answer to this, but nobody wants to lift their hand because this question has already been answered, right? Because someone answered, what is an example of antisymmetry? And another person answered, what is an example of transitive? Then the answer was the same, right? So, so let's talk about linear order, right? So the difference between linear order and a partial order is that partial order may not be defined between every pair of elements, whereas in a linear order, an ordering relationship is holds for every pair of elements, right? So again, the reason why we use the word order is because these types of relations represent some kind of ordering, right? So they mean that things are being done in a certain, there is, just like when we say A greater than or equal to B, we say that is represents an ordering, right? And B greater than or equal to C, that represents an ordering, right? So except that when we talk about greater than or equal to, that's an example where we have actually a total order, right? So if you take two integers, right? Say, integer n1 and n2, we know that either n1 is less than or equal to n2, or n2 is less than or equal to n1, right? So right? So can you think of another relation where this property does not hold? That is, two elements are there that you cannot compare, right? Here, what we are saying is that every pair of elements can be compared, and the result will be one is greater than or equal to the other, right? And then there are relationships where the elements are where the elements are not comparable. So what would be an example of that? So what was the other example I gave for antisymmetric and transitive?
Subset.
Right. So if I have two sets, A and B, can I say that? Right? That doesn't necessarily hold, right? So A and B may have nothing in common, in which case neither is a subset of the other. Or they may have a common intersection, but then they may have different elements after that. So the subset is an example of a partial order that's not a linear order, right? Whereas if you think about the greater than or equal to relationship on integers or real numbers and so on, those are linear orders, right? So every linear order is also a partial order, but some partial orders are not linear orders, right? So let's stop there. We are close to the end of the class. So if there are any questions, I will answer them. Otherwise, your recitation start at 4:30, and if you don't finish answering all the questions related to your homework during this recitation, then I will take the remaining questions on Thursday. Okay. Again, I'm here. You can ask questions. If not, you can hang up and take a break and go to your station.
Can you scroll up a little bit?
Sorry?
Can you scroll up? I missed one of the slides.
No, there's nothing. That's not done.
No,
so
up,
we are.
Up.
It stopped
the
here.
other way. Yeah.
Oh, you mean here?
Yeah. A little bit higher. Yeah, this one right here. Sorry.
Yeah.
Great, thanks.
Okay. Okay, very good.